Hello. Good afternoon, everyone. So this is our first class of physics optional today. In about, I think, maybe next 110 to 120 classes, we will do our physics optional as per UPSC syllabus. In today's class, I'm going to start, in a way, the first topic, which is classical mechanics. But we will not actually be doing classical mechanics for like at least I think next 2 or 3 classes. We'll be mostly doing mathematics. But even before I do mathematics, I wanted to briefly tell you about the subject itself. Okay, let's start with first looking at the syllabus of the topic, which we are going to discuss. We are going to look at all of these keywords which are directly given in the syllabus. A lot of the keywords which are not even directly given, but they fit into the scope of classical mechanics. We are going to discuss them also. So your syllabus essentially comprises of the first topic, classical mechanics and relativity. It comprises of 4 main themes, and within those 4 main themes there are a lot of things. So the first is mechanics of particles, and that includes, this must be the most familiar part of the syllabus because something all of you have already done in your school days or even in college. So laws of motion or conservation of energy and momentum. Maybe if you have not done physics in graduation, then maybe Kepler's laws, or maybe perhaps two-body problem and Rutherford scattering is something which might be like new to you if you have not done physics as your graduation subject. If you have done, for example, your engineering, it doesn't matter. All of these are very simple and very straightforward. Mechanics of rigid bodies, we will do this. This is actually a subject which can become very, very difficult, but our scope is very limited. So for UPSC, this is simple. But overall, in classical mechanics, this will be one of the difficult topics to complete. Same thing here also, fluid mechanics can be very difficult. So the third topic is mechanics of continuous media. And this includes 2 things. First, it includes the behavior of homogeneous solid under stress, which we call elastic behavior. So we'll learn about elasticity. And then we will do some of the topics of fluid mechanics. And the last topic is the introductory ideas about special theory of relativity. Okay. So this is the syllabus. And we'll come back to this syllabus part later. I briefly wanted to tell you about what type of subject this is and what is the scope of classical mechanics and how should we think about classical mechanics, how should we approach classical mechanics, what is the scope of classical mechanics as a subject. Like, let's start with that. So let me start with a very simple question, that when we come across this term classical mechanics, what does that mean? Like within physics, we say classical mechanics, what does it mean? I think very simple definition can be that all the branches of physics where we do not have to deal with quantum uncertainties. Like, so rather than having a definition separately for classical mechanics, I will define this with help of quantum mechanics. I'm of course going to discuss quantum mechanics in much more detail, and I will tell you the meaning of the word quantum uncertainty, that fundamentally what does it mean. We'll have a detailed discussion about it. But in one line, if I have to say classical mechanics, it is that all branches of physics where we do not have to deal with quantum uncertainty. So that includes Newton's laws of motion. That in fact even includes Faraday's and Maxwell's electromagnetic theory. And that of course also includes relativity, special theory of relativity by Albert Einstein. So all of that will fit into the definition of classical mechanics. Electromagnetic theory we have to discuss separately. Okay? Classical mechanics started with Newton. In fact, we can go a little bit earlier. So Galileo played a very important role in developing some of the earlier postulates of physics. But even those postulates were very limited, and that is why Newton is considered such a great name, because Newton was able to develop knowledge when very little existed. And he was able to discover things which are simply remarkable. And many of those things, even if they have been proven wrong, and many of the things which have been rectified, and many of the things which are not useful, but even then, Newton remains perhaps the greatest physicist who has ever lived. So a larger part of our discussion will be about Newtonian mechanics. That is our limited part of the syllabus. You both have studied physics in your graduation, so you already know that Newtonian mechanics is frankly not very helpful. After a point of time, you realize that Newton's laws are not very helpful, and I will prove this. Those who have not done physics in graduation, I'm going to prove this, that Newton's laws are not very helpful in when you actually want to solve problems of dynamics. And you realize that there are alternative methodologies which are much more elegant, much more beautiful, and simple. So for that, we have to use something called Lagrangian mechanics or Hamiltonian mechanics, and those two subjects would have made this entire discussion of classical mechanics even more beautiful. But ठीक है, for the purpose of UPSC, they are not part of the syllabus, so I guess you have to be happy about it कि हमारा syllabus कम है इस sense में कि हमको पढ़ना नहीं है. We do not have to study classical mechanics with help of Lagrangian or Hamiltonian. We only have to study Newtonian mechanics. Okay. Write down few things. I want you to write down few things first. Essentially everything for which quantum uncertainty is not important. The scope of classical mechanics includes, write down, the scope of classical mechanics includes scope of classical mechanics includes essentially everything for which quantum uncertainty is not important. So a lot of examples. Newton's laws, electromagnetic theory by Maxwell, all of that will fit into this particular definition. Write down, the laws of classical mechanics were originally written in laws of classical mechanics were originally written in vector form. Originally written in vector form. This is where it will seem classical mechanics the most intuitive. When you write, even there by the way it is not intuitive. I want to spend few minutes to talk about that how laws of physics, they do not have to be intuitive at all. But even within classical mechanics, this is perhaps where laws of physics will seem the most intuitive, right? So vector form in physical space, like in real space, Euclidean space, which we are familiar with. In physical space. So I can call it Newtonian mechanics. This is and our syllabus is restricted here. Our syllabus is only going to talk about Newtonian mechanics. But I definitely want you to know, write down a line in next paragraph. It is also possible to write down laws of classical mechanics. It is also possible to write down laws of classical mechanics in configuration space. Configuration space. That is Lagrangian formulation. अब ब्रैकेट में लिख लेना. Lagrangian formulation Lagrangian formulation, or phase space. This is called Hamiltonian formulation. I do not have to do these two things here, but I briefly wanted to mention few things about them. That when we do Newtonian mechanics, you realize that they're not useful, and the only way there can be at least little bit useful will be Cartesian coordinate system. The moment you change your coordinate system, you will realize that they become more complicated. By the way, they will become complicated even in Cartesian systems. But if I choose other type of coordinate system, they will become so much complicated that it will not make a lot of sense to do Newtonian mechanics. And you find more simple, elegant versions, and we do have those elegant versions, Lagrangian and Hamiltonian formulation. You will not escape them, by the way. Particularly, the Hamiltonian formulation, I will not escape this, even if it is not part of the syllabus. When I do quantum mechanics, I have to talk about Hamiltonian operator a lot, and I will tell you that how this Hamiltonian operator is associated with energy, right? So even though we are not going to discuss it here, which is frankly is like ideally UPSC should have included introductory part of the syllabus of Lagrangian and Hamiltonian, so that you can appreciate that why Hamiltonian occurs so much throughout quantum mechanics, okay? So, but you should know, I will briefly tell you in about 1 hour or maybe less than that in some other class about phase space, what it is. So it is an abstract space, and we can think of dynamics evolving into an abstract space which includes position and momentum of every particle which is part of a system, right? So it's an abstract space. It prima facie it looks very complicated, but it actually simplifies things a lot. And in fact, it simplifies things for those problems where Newtonian mechanics will not even be possible to do, right? So I wanted to re-emphasize upon this, that these two approaches, they simplify classical mechanics, but we do not have to read them. This is not part of our syllabus, okay? Write down in next paragraph. Maths is the language to write physical laws. Maths is the language to write physical laws. For the reasons unknown. For the reasons unknown. One of my favorite quotes in physics is by Paul Dirac. He is one of the pioneer of quantum mechanics. He is the person whose mathematical law allowed us to know about antiparticles. I will talk about antiparticles in detail in our particle physics classes, and Dirac was the person who essentially first theoretically showed that antiparticles can exist, and later it was proven to be correct. So Dirac has a quote, and I absolutely love this quote. Mathematics is a game where mathematicians invent the rules. Physics is a game where the rules are given to us by nature. What is interesting is that the rules of nature appear to be in the same mathematical rules as mathematicians have concocted. And we do not know. And we do not know why does it happen. So why nature speaks to us in the language of mathematics, we do not know. And that is why knowing about mathematics is important to appreciate physics as a topic. Okay, ये important है. So that is why for next 2.5 classes, or maybe even 3 classes, we'll be doing mathematics essentially. Okay? But I also wanted to tell you a few more things. That even though laws of physics are written in the language of mathematics, physics is not mathematics. What do I mean by that? So let's briefly talk about mathematics as a subject itself. Right? I'm not here to teach mathematics, but I do think that we should have a brief understanding about how mathematics as a subject has evolved. They say there is a very famous debate in mathematics, and that debate still has not been settled, by the way, that do we invent mathematics or do we discover it? Think about these two questions. There are a group of mathematicians who believe that the laws of mathematics, they are independent of human mind. They exist in some metaphysical realm, maybe, whatever. And human mind simply discovers them. Okay. That is one group of mathematicians who believe into this. This is called Platonism. There is a word given to it. I'm essentially telling you about philosophy of mathematics. Why I'm discussing philosophy of mathematics in physics, it will become clear within few minutes. But first let me tell you, there are three main branches. I will only tell you about two of them. The third one is not important for us. For physics as a subject, the third one is not important. The first is called Platonism. The second is called Formalism. And the third is called Intuitionism. Intuitionism. I'm not going to tell you about Intuitionism, but we should know about Platonism and Formalism. Platonism comes from Plato. Plato was an ancient Greek philosopher who believed that there are certain pure, remarkable ideas which exist in some other abstract realm. So for example, he considers that every pure human thought exists in some metaphysical realm, and we can aspire to be as close as we can come to that realm. So people use this in mathematics also, and there is a philosophy, there is a group of mathematicians who will say that they follow Platonism, which essentially means that they will say that they do not invent maths, they discover maths. Maths already exists and they discover it. Jaise, for a Platonist, think of pi, that have we discovered pi, or pi always existed and we simply now discovered it, or did we invent pi, or did we discover pi? Or think of some proof, some mathematical proof. Just I will give you, in number theory there are a lot of things which are still not proven. We know we do not have any exception to that, but they are not proven. Just one of the things which was proven recently, that for a fixed parameter, hexagon occupies the maximum area. This is a simple statement, that if I give you a fixed parameter, then among all other polygons, triangle and square and whatever, hexagon occupies the maximum area. This as a theorem has been there for more than 200 years. This theorem was only proven, I think, 20-25 years ago. But then we ask a question, that it has always been true or we just discovered it? So think about it. This will be a philosophical point to think, that this mathematical theorem which was proven in, let's say, 2000, was it not true before 2000? Or even if we had not proven this in 2000, would it not have been true even after that? So Platonists will say that the laws of mathematics have always been true. We simply discover it. Right? So when we discover some theorem, we are simply discovering it, right? One of the greatest name in Platonism, even though he himself did not use this word for himself, will be none other than Ramanujan. And his mentor, G.H. Hardy. Hardy और Ramanujan की कहानी पढ़ा ना आपने? Hardy, he received some letter by Ramanujan and he invited Ramanujan in England. So Hardy and Ramanujan, so for example, Ramanujan talks about that when he writes his infinite series, he essentially, people ask him that how do you know this is true? And he does not present any proof. He simply tells you that, look, there is a formula of 1 by pi and there is an infinite series here, that some n is equal to 0 to infinity, and there will be a very complex looking formula here, something like this. And there is no proof of it. And if you expand this series, you realize that, yeah, it is actually converging to 1 by pi. And people asked him that where do you get these ideas? And his answer was that his goddess, Namagiri comes in his dream and tells him all of these mathematical equations. So Hardy was, for example, a very strong believer in that we do not invent math, we simply discover maths. Okay? This is one branch of mathematicians, and most of the mathematicians, even though they will not readily accept it, deep down they are Platonist. Deep down they would want like they are Platonist. Then you have formalism. Formalism के जो champion है वो Hilbert है. So let me write some names also here. Hardy, Ramanujan, Hilbert. Hilbert will also come in physics, by the way. We'll talk about Hilbert in physics also. So Hilbert was a great mathematician, a great physicist. And in 1900, Hilbert essentially said that why are we putting mathematics on such a high pedestal where the laws of mathematics have to exist into some metaphysical realm? Hilbert did not agree to that. For Hilbert, mathematics start with certain axioms that when we look at specific branch of mathematics, we start with certain self-evident truths which do not have any proof. We call them axioms. Everybody is clear about the meaning of the word axiom? So there are self-evident truths. For example, between 2 points, I can always make a straight line. I cannot prove this, but this is a self-evident truth, so I will call it axiom. So for Hilbert, mathematics starts with certain axioms, and from those axioms, we can develop different theorems as long as they are consistent with those fundamental axioms. That was Hilbert's belief. Now, you may see it, you may think that this does not seem like as beautiful as what Platonists think, but this is also quite remarkable because it makes mathematics independent from that burden of that there is some deep reality in the nature and it is job of mathematicians to figure out that deep reality. So that burden is not associated with if you are a formalist in your approach. As long as your rules are consistent with the fundamental axioms, then that's perfectly fine. Yes, I will give you a fantastic example. Euclid, many years ago, developed axioms of geometry. हम बचपन से Euclidean geometry हमने पढ़ा हुआ है, ठीक है? Then in 19th century, you have a German mathematician, his name is Riemann. And Riemann imagines a curved space. And then he writes, he imagines that there is a curved space. And he imagines that how then line will look like, or shapes will look like, or how laws of mathematics will look like in a curved space. Now formalists will have no problem with this, because as long as it is consistent with the axioms you started with, doesn't matter. So that is what I am trying to say, that mathematics does not have to have that burden of that it is discovering some deep reality of the nature. This is the belief of formalists. In fact, Hilbert was a person who wanted something similar for physics. That the same way, so Hilbert made a very famous conference in early 20th century, where he wrote down all of the axioms of mathematics, known axioms of mathematics. And he wanted something similar for physics, that maybe even for physics we can start with certain axioms, and then all of the laws of physics are derivable from those axioms. And this is where I will go back to a statement I made, that physics and maths are not same. That physics is a science, mathematics is a tool. And ये distinguish factor जो है, distinguishing factor है, बहुत ज़रूरी है. That mathematics should be used as a tool, because in mathematics there are always absolute truths, which we are calling axioms. In physics, nothing can be taken to be absolute truth, because the very fundamental definition of science starts with doubt. I can have a physical law which is very much true in a particular domain, but that physical law will not make any sense in some other domain. If I try to apply Newtonian's laws in quantum mechanics, it will not at all work, but Newtonian law will work perfectly fine in the domain of classical mechanics. So I will re-emphasize upon this line that physics, the language of physics is maths, but physics is also not maths. It is very, very different from maths also. By the way, just before I come back to physics, I should tell you that another mathematician in 1960s, his name was Winger, and Winger wrote a very famous paper. And in this paper, he essentially increased the weightage of Platonism as a branch of philosophy of mathematics. So think of some of the ideas which were invented in mathematics. So think of complex number. Complex number was invented as a tool to solve cubic equations in mathematics, somewhere in 15th century. Now we cannot do quantum mechanics without complex numbers. अभी हम quantum mechanics करेंगे, I think कुछ classes के बाद we'll start our quantum mechanics, and you will find that quantum mechanics cannot be done without complex number. ठीक है? Second example I will give you, that Riemann geometry I told you. Riemann imagined a curved space, and then he is writing rules of mathematics in a curved space, not in a Euclidean space, but in a curved space. And then Einstein writes few decades later, his general theory of relativity. And in general theory of relativity, near a very heavy object, the space-time has curvature. So now Riemannian hypothesis, all of that what Riemann did, we have to apply that for general theory of relativity. And general theory of relativity is one of the most fundamental laws of physics. So indeed in this case, that mathematics is telling you something about the reality of nature, right? And I can give so many examples. Third example, which we do not have to do, there is a branch of mathematics called group theory, right? Group theory mathematics becomes very abstract. Group theory is essentially about symmetries of different groups. And then you use group theory in particle physics, in standard model of particle physics, where you are talking about symmetries, and you are associating that with conservation laws, right? And you are talking about selection rules with help of group theory. So we have so many examples where how laws of something which was developed just for the sake of mathematical curiosity, and all of them found some sort of application into physics, right? Ramanujan, some of his functions, they have applications in string theory, one of the most advanced branch, very theoretical, one of the most advanced branch in physics, which aims to unify two very diverging branches of physics. One is general theory of relativity, another is quantum mechanics, right? So I will tell you briefly about that also, like why I said that these are two diverging branches of physics, general theory of relativity and quantum mechanics. So the point I'm trying to make here is that even though we should be very clear about two things. First, we still do not know that why language of physics is maths, right? Maybe there is some deep mathematical reality of the nature and we have to discover it. Maybe there is not, right? But even if there is one, we cannot think of physics as a mathematics. We cannot think of physics same as mathematics. A lot of things, they are very beautiful in mathematics. Does not necessarily mean that they are also true in the sense that they're explaining some physical law of the nature, right? Because this is a problem which many physicists have. Just say, one of the most smartest person right now who is alive is Dr. Roger Penrose. And Dr. Roger Penrose is a very huge critic of string theory. He is a Nobel laureate who first talked about black holes. Not first, but he essentially proved mathematically that black holes can exist. And Roger Penrose is the biggest critic of string theory. And his main criticism is that people who are writing string theory, they want to believe in it because the mathematics is very beautiful. And the mathematics is so beautiful, they want it to be true. But that is not a good metric to decide that if a particular law of physics is correct or incorrect. So I wanted to emphasize upon this, again, that physics needs maths as a language, but physics also is not maths. I cannot have axioms in physics, and based on those axioms, we can essentially derive all of the laws of physics. We cannot have that. So Hilbert tried to do that in 20th century, and even after more than 100 years, we still cannot do that, okay? So there are different realms of physics. We should know about those realms. Those realms have boundaries, And those boundaries are very weird, but within a realm we have our own laws, and those laws are beautiful. So for example, let me tell you the 4 main realms of physics. First I will start with non-relativistic classical mechanics. Okay? We have to, and I already told you that there are 3 different approaches to do this. For our purpose, we only have to do the first one. We only have to do Newton's laws of motion. So non-relativistic classical mechanics. Then as we go to smaller size atoms, molecules, subatomic level, but not at very high speed, you get this non-relativistic quantum mechanics. Relativistic का मतलब ये है that particles are traveling with speed much less than speed of light. If I am using the word non-relativistic, that something speed of something compared to c, that is much less than 1. That is the meaning of the word non-relativistic. So non-relativistic quantum mechanics will mean that even if, let's say, I choose electron का speed I am assuming to be, let's say, 10 to the power 4 meter per second or 10 to the power 5 meter per second. So compared to speed of light, which is 10 to the power 8, it still is very less. We have to do this. In quantum mechanics again, we only have to do non-relativistic quantum mechanics. Okay? Then we have relativistic classical mechanics. We will be dealing with things which are traveling with very high speed, but we will not make any quantum assumptions. This does not help beyond a point. Relativistic classical mechanics, so people like Maxwell, they are the pioneer in relativistic classical mechanics, but it does not help beyond a point. The best theory to describe reality as we know of is relativistic quantum mechanics, and इसी का जो एक advanced version है, that advanced version becomes quantum field theory. Quantum field theory is the best description of nature at microscopic level. हमको पढ़ना नहीं है. I'm simply telling you as a branch of subject that this exists. And in quantum field theory, there are different type of fields which are much more important than the particles we associate with them. For example, in quantum field theory, electron is an excitation in electron field. Photon is an excitation in electromagnetic field. Because when we started physics, we started with talking about particles, and then we thought about fields, and we thought that fields are necessity, mathematical necessity. Now we know, or now we think, that those fields are much more important than the particles themselves. So we do not have to do that. We do not have to do quantum field theory, but we do have to do this, we have to do this, and we have to only introduce ourselves to spatial theory of relativity. Okay? What about the boundaries between things? We can ask a question that where does non-relativistic classical mechanics start and this ends and this starts? And the answer is it's not a fixed boundary. It's a very diffused boundary. We do know that as long as V by C is very less, even if I totally ignore relativistic effect, my laws will not be affected, my predictions will not be affected. As this V by C starts coming closer and closer to 1, and if I am still ignoring relativistic effect, then my accuracy will not be very good. And if I keep doing that as it approaches closer and closer to 1, my accuracy will worsen and worsen. So it is not a fixed boundary. It is a very diffused boundary. Similarly here also, I will answer this question in statistical physics, that where does classical mechanics end and quantum mechanics start? At what level, at what small, we say that atoms and molecules and subatomic particles are guided by quantum mechanics. Bigger particles are guided by classical mechanics. But at what level? Is it 10 to the power minus 5 meter? Is it 10 to the power minus 6 meter? Is it 10 to the power minus 7 meter? So we have to answer this question, that at what level we can say that quantum uncertainty is not playing a role, and at what level it does play a role. So those boundaries are very interesting and very complicated also. We do not have to do those boundaries problem. Here in our syllabus, we have to talk about one specific realm, and in every realm you will find that we have laws, and for that realm those laws are working perfectly fine, and they are describing evolution of a system with respect to time in a very nice manner. Okay? Write it down. Boundaries between regimes, boundaries between regimes, are interesting and complicated, but within a boundary, we can find effective models. We can find effective models to describe nature. Write down the next paragraph. In physics, there is a quest towards, reducing the number of independent physical laws. There is a quest towards reducing the number of independent physical laws. So we call this unification. Let me give you a few examples to justify this statement what I have just made. Electricity and magnetism was discovered separately, but they were combined into one theory, electromagnetic theory. Light as a phenomena, optics as a subject, that developed separately, we combined that into one. Then we focused upon that what are some of the fundamental forces which describe the evolution of the nature. And we came across 4 fundamental forces: gravitational force, electromagnetic force, strong interaction and weak interaction. Now there is a quest towards, the ultimate quest in physics right now, that can we combine all 4 fundamental forces into one theory. And this is something which has become the most difficult problem as of now, and also the most sought after problem. So because if I talk about electromagnetic theory, if I talk about strong interaction, weak interaction, all 3 of them are described by quantum mechanics. If I do gravity, that is described by Einstein's general theory of relativity, not Newton's. Newton's laws are only approximation of Einstein's general theory of relativity. These 2 are very correct in their own realm. So if I have to describe behavior of stars and galaxies and planets, I have to use general theory of relativity. if I have to describe behaviors of atoms, molecules, subatomic particles, I have to use quantum mechanics. And both of them are very successful in their own domain. But if you try to combine them into one framework, you fail at it. One can ask a question that why do we have to combine them? Because in scientific method, nothing is stopping us in saying that look, this is how laws of nature are written. That laws at nature at very large scale is described by general theory of relativity, at very smaller scale is described by quantum mechanics. Why do we have to combine them? So we have to combine them because of few problems. The problem to understand singularity, the center of a black hole, or the Big Bang itself. That when we say universe started with a singularity, that this infinitely dense object, what do we mean by that? Or think of the center of the black hole, which we say singularity. So very small but very heavy. Very small, we have to use quantum mechanics. Very heavy, we have to use general theory of relativity. So if you want to understand that, you need to have a theory which can combine quantum mechanics and general theory of relativity, which can combine all four fundamental forces into one. Such theory will be called theory of everything. This is the ultimate quest in physics right now. One of the candidate of theory of everything is string theory, which I was just talking about. But even string theory, like there are few people who want to believe in it, but then there are many people who simply say that it is not verifiable and we should not like run after it just because the mathematics is beautiful. I just gave you the example of Dr. Roger Penrose. तो यहाँ पे आप example लिख सकते हो. For example, unification of four fundamental forces. Unification of four fundamental forces. Unification of four fundamental forces. You can write down more. Electromagnetic interaction. Strong interaction. We will talk about all of them in detail in our particle physics class. Strong interaction, weak interaction, weak interaction, can be explained by quantum mechanics, but gravity requires general theory of relativity. General theory of relativity. You can add a line. Both quantum mechanics and general theory of relativity and general theory of relativity general theory of relativity are very successful in their own domain, very successful in their own domain, but any attempt to combine them into one theory, has proven to be futile. Such theory, if developed, can be called theory of everything. Such theory, if developed, can be called theory of everything. Okay, so this is this is the ultimate quest regarding unification. As I said, that there is a quest towards unifying laws of physics, that lesser and lesser laws, and the ultimate quest is to find the theory of everything. So things like string theory or quantum loop gravity, these are some of the candidates, but they have their own set of problems. Okay, so all of these big talks. Now let's come to the main agenda. Let's start our classical mechanics discussion. But before that, we will do some maths here. We'll do, like, about this class and next 2 classes, we'll only do maths. Okay. But before I proceed to the maths, if you have questions in like whatever we have discussed, something you'd want to add, something you want to ask, you can go ahead and do that. For classical mechanics, the book I recommend, I already have mentioned in the previous session, is by Klepner and Kolenko, right? One of the reasons why this book, because perhaps one of the best book of classical mechanics is written by Goldstein, but that largely includes Lagrangian and Hamiltonian, which is not part of our syllabus. So that is why read Klepner and Kolenko, right? It's no Lagrangian, Hamiltonian is mentioned anywhere, except few parts. It covers your syllabus in entirety. Jaise, it does not have any dedicated chapters on elasticity and fluid mechanics. So that will be something, koi baat nahi, jitna hum class mein karenge wo enough hoga. Similarly, it does not have a dedicated chapter on things like field and potential, gravitational field and potential. So that is also something that can be done from DS Mathur, for example. But we will do all of those topics in the classes, right? But otherwise, very beautifully written book, and I highly recommend that if you have time, then please read that book, right? And almost all of the chapters are important in Klepner and Kolenko. Classical mechanics builds the foundation of each and every subject, even including quantum mechanics. The language of quantum mechanics is very different from classical mechanics, but that foundation is very important. So that is why having a very good hold on classical mechanics is important for all other coming subjects which we will have in future. Okay? So if you have something to ask here, you can ask questions before we jump into our topics. Okay, so give this heading, vector algebra. Let's start with our first topic. We will do first vector algebra, then we will do vector calculus. These 2 topics, and we will understand different coordinate systems. We'll develop a visual, intuitive understanding of Cartesian, we all know, but I want all of you to have a very good visualization of cylindrical polar coordinate system, and more importantly, spherical polar coordinate system. So when I tell you spherical polar coordinate system, it should be as simple as writing x, y, z in Cartesian coordinate system. So because you'll find that in many other, not just in classical mechanics, but in many other topics, that understanding of spherical coordinate system will be very important and very useful. Okay? So the first topic, so we'll only do 2 topics here, vector algebra, vector calculus, in all coordinate system, not just Cartesian, but in spherical and cylindrical polar coordinate system also. Vector algebra. Let's start with that. Okay, we all have learned that high school definition of vector and scalar. What was scalar? Only magnitude. What was vector? Both magnitude and direction. So the first thing I want to say here, that this is not a good definition. Both of this, not just for scalar, not just for vector. Even for scalar, this is not an adequate definition, that scalar has only magnitude and vector has both magnitude and direction. I can ask few questions, for example. Direction with respect to what? When we say direction, direction with respect to what? So you say that, okay, from some reference point. But why you chose that reference point? Are you saying that this reference point is more special than some other reference point? So for example, let's say you have to describe some vector, and you say that in my frame of reference, this is a vector. But why I have to choose your frame of reference? Why can't it be my frame of reference? Her frame of reference. So that's the point. That if I'm saying direction, then direction with respect to what? Right? Because there is no one frame of reference which can be considered. This is a special frame of reference. So that is why this is not an adequate definition. First. Second problem, look at the definition of scalar. I give you this. I give you a vector, r. Okay? I give you coordinate system also, x and y. And this r essentially is this xi. I generally will use this x cap. For unit vector, I will generally be using this. Rather than using I, j and k, I will be using x cap and y cap. Because I want to be very, like the moment I use that cap, it should be very clear that for what I am using this unit vector for. Okay, so x cap plus y cap. Okay, so what about that mod x? Is this mod x a scalar? I'm asking a question. Is the mod x a scalar? Like in our traditional definition, is it a scalar? Of course it is. It has a magnitude. But I'm telling you that that is not correct. Mod x is not a scalar. It is not also a vector. That the question of vector and scalar is not a suitable question to ask only for mod x. Right? The moment I give x, then that is a vector. X is a vector. Right? So what is, and if I, in R xx plus y cap, mod x, is it a vector? The answer is no. It is not, sorry. Is it a scalar? The answer is no. It is not a scalar. So we have to redefine both vector and scalar. But we can, you can ask a question that why are we doing this? Why are we redefining this concept? So I have a very simple answer to that question. First, remember I told you that in mathematics we start with certain axioms. But forget about the mathematics part. Even come to the physics part of things. I write Newton, I am doing essentially Newtonian mechanics. I told you that Newtonian mechanics were written in form of vectors. That was my starting point of classical mechanics, that Newton's laws and Newtonian mechanics is written in form of vectors. But laws of physics, whatever law I write, that law should not depend upon frame of reference. Can we agree upon that? That law should not depend upon frame of reference. We all have to agree upon this simple thing. Just I will give you a simple example. Let's say this is a frame of reference S. And this is some other frame of reference S dash. And they both are describing some particle of mass m. Okay? S and S dash में कुछ relationship है, I do not even know that. But both S and S dash, if they are describing this particle m, they both have to agree that for S, F is equal to ma, and for S dash, F dash is equal to ma dash. Do you see the point? That even if S and S dash are measuring different acceleration, they are measuring different force as a result of that. But the form of the law, that force is equal to mass times acceleration. This is Newton's second law. It is one of the most fundamental laws in classical mechanics, that force is equal to mass times acceleration. If I have a system whose mass does not change, then force is equal to mass times acceleration. So maybe A and A dash are different, F and F dash are different, but that form has to be the same. And I'm writing force is a vector, acceleration is a vector, F dash is a vector, A dash is a vector. So I have to represent my quantities, and in this case the quantities are vector. I have to represent my quantities in a way that they encode that transformation property. If I shift from S to S dash, then how a vector changes, that information should be encoded in the vector itself. I do not have to write it separately. So I have to redefine my vector in a way that if I transform a vector from one coordinate system to another coordinate system, the transformation law should be encoded inside it. If it is not encoded inside it, then my form of law, f is equal to ma, f is equal to ma dash, f dash is equal to ma dash, that form will start getting distorted. I do not want that, right? My values can be different, but my form of law must be the same. We call this invariant property. This is very important, and ये throughout our discussion of physics मैं बार बार इस term पे आऊँगा, that my laws of physics, they have to be invariant. They should not depend upon a particular frame of reference. I measure something, you measure something. We both can disagree. जैसे एक simple सा example ले लो. I can disagree upon how much kinetic energy a particular object has and how much potential energy that object has. You also will disagree upon it. आप किसी और फ्रेम में उसका स्पीड मेजर कर रहे हो. But we both have to agree upon simple thing that if there are conservative forces, then that kinetic energy plus potential energy will be constant. ये change नहीं होना चाहिए. So this is what I mean, that when I write laws of physics, they have to be form invariant. That even if I'm measuring into different coordinate system, they should be same. And because of that, if I'm writing this into vector form, then that vector should encode how it transforms from one coordinate to another coordinate system. Write down few things here. पहले तो आप ये लिख लेना. This is not an adequate definition. This is not an adequate definition. For example, direction with respect to what? Direction with respect to what? As there is no preferred coordinate system. As there is no preferred coordinate system. There is no preferred coordinate system. Write down in next paragraph. Laws of physics. Laws of physics should have the same mathematical form. Should have the same mathematical form should have the same mathematical form when expressed in different reference frames. When expressed in different reference frames. Thus, physical laws are expressed in terms of covariant quantities. I'm using a word here. Covariant quantities, so that they remain form invariant. So that they remain form invariant. Form invariant. तो covariant का मतलब यहाँ पे ये है that if I have a vector or a scalar for that matter in S, that same vector, how it will look like in S dash, or that same scalar, how it will look like in S dash, I should have a law for it. You understand the meaning of it? That the meaning of the word covariance here is that A is different in S and S dash. That's fine. That's fine. But if I give you S and give you S dash, and I give you the relationship between S and S dash, that how S and S dash are dependent upon each other, then I should be able to derive that how A and A dash will be dependent upon each other. That is the meaning of the word covariance. That covariance should occur in a way that my law is form invariant. That F is equal to MA in S, F dash is equal to MA dash in S dash. So this is very important. अभी तो बहुत सिंपल सा एग्जाम्पल है. अभी हम इलेक्ट्रोमैग्नेटिक थ्योरी में आएंगे, दिस विल बिकम मोर कॉम्प्लिकेटेड. हम थ्योरी ऑफ रिलेटिविटी में हम बात करेंगे, दिस विल बिकम मोर कॉम्प्लिकेटेड. That what changes, what remains same, this will be one of the most important question to ask in our discussion of theory of relativity. Because in theory of relativity, our very notion, our very intuition of space and time will be challenged. And even when that space and time intuition is challenged, we still ask this question, what is not changing? And we'll realize that this will be speed of light. The speed of light is not changing, but then our notion of space and time, that is changing. So ये जो अभी मैंने बताया अभी, that laws have to be form invariant, this is a very important point, and it will keep propping up as we go into other topics also. ठीक है? So how should we do this then? How should we redefine vector then, right? So आप एक लाइन लिख सकते हो, physical quantities must carry their own transformation law. Physical quantities must carry their own transformation law. Their own transformation law. So even vector has to go through certain type of things. I can tell you all of the axioms related to vector. Remember, we are discussing a topic of mathematics here. I can tell you one axiom that if I do this, A plus B will be same as B plus A. What do we call this? Commutative law. I do this, A plus B plus C, it will be same as A plus B plus C. What do we call this? Associative law. So I can tell you all of the axioms, but I want you to tell you the most fundamental transformation law involving vector, and that involves if I rotate my coordinate system. And for simplicity, I'm going to right now start with 2D system, 2D plane. We will generalize that to 3-dimensional later, but I'm only going to focus upon 2-dimensional plane. So imagine there is a 2-dimensional plane. I have x-axis and y-axis, and then I have a vector. But let's say, in fact, before I draw a vector, let's say that I rotate this coordinate system by some angle theta. Okay? And this x becomes x dash, and I rotated this also, this is also angle theta, and this y becomes y dash. And now I'm describing a particular point. Let's call this point P, this is O, and this OP, if I measure this OP in xy, then this is vector R. Okay? And if I measure the same OP in x dash y dash, then this is vector R dash. ठीक है? अब immediately आप एक ये चीज देख सकते हो कि भले मैं ये S में मेजर करूं, let's say कि xy जो है वो S है, ठीक है, and x dash y dash जो है वो S dash है. तो जो R length है, either I measure this in S or S dash, it will remain R. ये हम एग्री करेंगे ना कि xy प्लेन में हमें लेंथ मेजर करें, x dash y dash में करें, it remains R will be same. That mod R will be same as mod R dash. Now this is scalar. So this is the definition of scalar. That even if I rotate I will make you write all of this. Just make the diagram right now, but I will make you write all of this. That even if I rotate my coordinate system, and a quantity which does not change while keeping the origin intact, those quantities are scalar quantities. So that is why that mod x is not a scalar quantity, because यहाँ पे जो x dash है वो ये है x डैश पे, और y जो है वो y डैश जो है वो ये है. इज x सेम एज, और यहाँ पे x ये है और y ये है. इज x सेम एज x डैश? नो. इज y सेम एज y डैश? नो. So x is not a scalar, y is not a scalar, but is r same as r dash? Yes, that is the correct definition of scalar. Now, what is the correct definition of vector? पहले आप write down the definition of scalar. Make this diagram. If we rotate the axis, keeping origin unchanged, if we rotate the axis, keeping origin unchanged, keeping origin unchanged, distance to any point, distance to any point, and distance between points, and distance between points don't change, don't change. The correct definition of scalar will be, write down a quantity which does not change in magnitude, which does not change in magnitude, which does not change in magnitude under such rotation is called scalar. Which does not change in magnitude under such rotation is called scalar. So now you can think of all of the scalar quantities and you can define, use this definition. That does mass change if I rotate my coordinate system? No, it does not. Does energy change if I rotate the coordinate system? Total, no, it does not. So now I can use this definition at multiple places and you'll realize that, okay, all of these things are scalar quantities. Okay. What about vector quantity? So to appreciate vector quantity, I would want you to first find out the relationship between x dash x. I'm giving you this problem. I'll give you 2 minutes to solve this. How can we write x dash in form of x and y dash and theta, and y dash in form of x and y and theta? This is a problem of trigonometry. I will give you 2 minutes to solve this. Is the diagram clear? I will give you a hint also. इसको phi मान लो, इस एंगल को आप मान लो phi. एक मैंने 2 चीज़ बताई थी आपको. एक एक्स्ट्रा नोटबुक हमेशा लेके आना क्वेश्चन सॉल्व करने के लिए. ऑलवेज डू दिस. आई इनफैक्ट स्टूडेंट्स ऑनलाइन हु आर ऑल्सो वॉचिंग इट, सो आप फेयर बाद में कर लेना इसको, और जो एक्स्ट्रा सोल्यूशन है उसको आप जो भी आप कट फट होगा वो आप दूसरे नोटबुक पे कर लोगे. If you need a hint, I can give you a hint. You can use polar coordinate system. X is equal to the fact that x is equal to r cos theta and y is equal to r sin theta. That will solve the problem fastest. But अब बाकी भी तरीके, बहुत सारे तरीके हैं, आप कोई भी तरीका यूज़ करो. I want you to find out how x dash can be written in the form of x, y and theta, and same thing for y dash. कर लो, जो भी कोई भी तरीका यूज़ कर लो. You can use vector projection, that's perfectly fine. A vector projection यूज़ कर लो, whatever method you want to use it. प्रोजेक्शन के लिए you need dot product, and I have not even defined dot product. प्रोजेक्शन के लिए हमको डॉट प्रोडक्ट चाहिए होगा ना. डॉट प्रोडक्ट तो मैंने डिफाइन ही नहीं किया है, बट आपको पहले से पता है डॉट प्रोडक्ट, तो आप उसको यूज़ करके कर सकते हो. Just want you to find out the relationship. डायग्राम में ज़्यादा अच्छा बना देता हूँ मैं ताकि रख दीजिए, एक चाय बोलिएगा लेते हैं. Okay, so this is the textbook I was talking about, Introduction to Mechanics, Kleppner and Kolenko. And I told you that in every class bring a calculator. So this is the calculator I use. This is Casio FX991 ES Plus. Let me write it down. हम जितना जल्दी कैलकुलेटर से खुद को एक्वेंट कर ले उतना बेटर है. हाउ टू यूज़ दिस कैलकुलेटर इफेक्टिवली. एग्ज़ाम में सिंपल अरिथमेटिक कैलकुलेशन से हमारा टाइम वेस्ट नहीं होना चाहिए. सिंपल सा बात. दिस इज़ अलाउड, कैलकुलेटर इज़ अलाउड एंड यू नीड टू नो हाउ टू इफेक्टिवली यूटिलाइज. एनीवेज ये हुआ ये. डू यू नो द आंसर टू दिस क्वेश्चन बाय द वे? होता क्या है ये? डू यू नो हाउ एक्स डैश एंड वाई डैश विल बी रिलेटेड? X dash will be, let me use small x, x cos theta plus y sin theta, and y dash will be minus x sin theta plus y cos theta. ये आएगा आंसर आपका. सिंपल सा तरीका है. आप इसीलिए आई गेव यू दैट हिंट. थिंक ऑफ फर्स्ट इन एक्स वाई. इन एक्स वाई जो x है वो क्या है? r cos phi है and y is r sin phi. We already know tan phi will be y by x. Phi is tan inverse y by x. We also know that r is equal to, I can write few more things. Phi is equal to tan inverse y by x, and we also know that r is equal to square root of x square plus y square in xy. In x dash y dash, same thing, but rather than phi, this becomes phi minus theta. So if I choose this as r dash, then r dash projection on x dash is r dash cos phi minus theta, and on y dash it is r dash sine phi minus theta. Is that clear? That this is r cos theta, sorry, r cos phi, this x here was r cos phi, and y here was r sine phi. X dash here is r cos phi minus theta, this angle, r cos phi minus theta, and y dash here is r sine phi minus theta. So x dash, let's call this r dash first, r dash cos phi minus theta, but I just already have shown that r is a scalar, that mod r and mod r dash is same. तो इसको आप expand करके देख लो, r dash को हम r लिख लेते हैं, and this is cos phi cos theta plus sin phi sin theta, and I just told you, sorry, cos theta cos phi. R cos phi is nothing but x, so this is x cos theta, and r sin phi is nothing but y, so this is y sin theta. Okay? And similarly I can do the same thing for y dash. Y dash is equal to r dash sin phi minus theta, which is r dash sin phi cos theta minus cos phi sin theta. And r dash sin phi, ये क्या था? Y cos theta, and r dash cos phi, what was that? X sin theta. तो इसी को ऐसे लिख देते, थोड़ा सा rearrange कर देते. This is minus x sin theta plus y cos theta. ठीक है? ये correct definition of vector है. That if I write a vector, remember I told you that vector, my laws of physics have to be form invariant, and for that I need covariant quantities. Covariant quantities mean that I should know a transformation law from one frame of reference to another. And not just I should know, my quantity in itself should encode that information, right? So what I'm essentially saying, that if I write this in matrix form, this is x dash y dash, what will be this 2 by 2 matrix? जल्दी से बताना मुझे, क्या होगा यहाँ पे? एलिमेंट्स क्या क्या आएंगे? cos theta sin theta minus sin theta and cos theta. पहले तो आप क्लियरली सबसे पहले देख लो, ये यूनिटरी मैट्रिक्स है, इसका डिटर्मिनेंट आप लो क्या है? cos स्क्वायर थीटा प्लस sin स्क्वायर थीटा, सो इसका डिटर्मिनेंट 1 है. सो आई गेट अ 2 by 2 and I can call it rotation matrix. Unitary, in fact it is unitary rotation matrix. Write down, this is a linear transformation. I hope everybody knows, since I am doing a simple matrix multiplication, this is a very good example of linear transformation. There are no quadratic terms involved here. This is a simple linear transformation. Write down a line, in two-dimensional space, any quantity u which transforms the same way as R is transformed, is vector. Now this is the correct definition. that vector has magnitude, vector has direction, and vector follows this transformation law that if I have two frame S to S dash, which I have got after rotating this S by angle theta, then that ux dash should be ux cos theta plus uy sin theta, and that uy dash should be minus ux sin theta plus uy cos theta, and in matrix form this rotation matrix should be same. अब ये मेरा कंप्लीट डेफिनेशन ऑफ वेक्टर. दिस इंक्लूड्स बाकी सारे ट्रांसफॉर्मेशन इसमें इंक्लूडेड है. इफ इट इज ट्रांसलेशन वो भी इसमें आ जाएगा. एस एंड एस डैश के बीच में ट्रांसलेशन है. दिस इज इनकोडेड हियर. दिस इज द मोस्ट जनरल ट्रांसफॉर्मेशन a vector has to follow. If I change from one coordinate, remember no coordinate system is preferred coordinate system. So if I change from one coordinate system to another coordinate system, this is how my vector should transform in two-dimensional space. I do not know how this will happen in three-dimensional space right now, but I can make an argument that in three-dimensional space, मैं लिख सकता हूँ in three dimension, that ux dash, uy dash, uz dash, it should be some 3 by 3 matrix. I do not know what this matrix is right now. In fact, this matrix will be much more complicated for a general transformation. For a very specific transformation, it's a very simple matrix, but for a general transformation, this will be a very, very complicated matrix. We have to deal with this matrix once in our rigid body dynamics class. I will tell you, I will do this problem, but not right now, in rigid body dynamics classes. There I have to multiply 3 different 3 by 3 matrices to find the final answer. And it should be ux, uy, and uz. So I should have some 3 by 3 rotation matrix, and it should be again a unitary matrix. I can say that also, that this should be a unitary matrix. इसका जो determinant है, that should be 1. I do not know what it is, but the same definition which I used for 2D is also applicable for 3D. So whatever that general matrix looks like for R, x, y, x dash, y dash, z dash, all other quantities who follow that same law, same transformation law, all of those quantities are vector. And now I write my laws of physics in vector, and that vector already has that encoded information that how it transforms from one coordinate system to another coordinate system. This is a very important idea which will keep propping up, that I have to write laws of physics in form invariant, right? Give this heading. Achha, by the way, you already know many properties of vector. I already wrote few of them. So for example, I know a plus b is b plus a. This is called commutative property. I also know that a plus b plus c is a plus b plus c. This is called associative property. And if I multiply this with a scalar, then I multiply with both of them. So with respect to scalar, scalar multiplication is distributive. इसको हम क्या बोलेंगे? Scalar multiplication distributive. Give this heading dot product. Dot product. So forget about physics. Let's approach this only with help of mathematics. That we are doing vector algebra. In vector algebra, we have certain axioms about vector, and I want to build that how this term, how this quantity which I'm calling vector, how this will behave. So I want to answer a question that if I take two vectors, with help of two vectors, can I produce a scalar? Forget about जो भी है, जैसे I don't buy this as the starting point as a good definition. जैसे हम सबने तो यही पढ़ रखा है ना बचपन से, that A dot B is AB cos theta. बचपन से तो वही पढ़ते हैं. I will not use that definition. I will now use my transformation definition which I just mentioned. I will start with a question first. And I'm again only sticking to 2 dimension right now. I'm not going to 3 dimension. That if I give you 2 vectors, then can you produce scalar? And in how many ways you can produce scalar? Okay? Let's say if I give you just vector A, and I ask you that can you produce a scalar from this vector? Turns out I can. आप ये ट्रांसफॉर्मेशन लॉ यूज करके देख लेना. ये a डॉट ए एक्स स्क्वायर प्लस ए वाई स्क्वायर है. आप एक काम करो, ट्रांसफॉर्मेशन लॉ यूज कर लो, जहाँ पे a हैज बिकम a डैश इन s डैश, दिस हैज बिकम a डैश इन s डैश, this has become ax dash square, ay dash square, and you will find that it will be same as ax square plus ay square. If I take vector b, this is also scalar. But if I take this quantity, ax bx plus, turns out this will also follow your scalar law. Write it down. In two-dimensional space, for two vectors A and B, we define A dot B as this. This is a scalar. Write down, this is a scalar. तो मेरा देखो starting question क्या है? That can we produce scalar from vectors? If I give you two vectors, how many scalars you can produce? I can produce 3 scalar. I can produce A dot A, I can produce B dot B, and I can produce A dot B. I want you to spend a minute in showing that this is a scalar. Do this calculation. आप अपने रफ नोटबुक पे कर लो. जो ट्रांसफॉर्मेशन लॉ है हमारा, स्केलर होने के लिए क्या होना चाहिए था? स्केलर होने के लिए A डॉट B का जो मैग्नीट्यूड है वो सेम होना चाहिए even if I go into from S to S dash. Even if I have rotated from S to S dash by angle theta, जो A dot B का मैग्नीट्यूड है वो सेम होना चाहिए. And I already know that what AX dash, BX dash, AY dash, BY dash will look like in terms of AX, BX and theta. आप करके देखो, आप देखोगे कि सारे थीटा वाले टर्म या तो कैंसिल आउट हो रहे हैं, ना तो cos स्क्वायर थीटा प्लस साइन स्क्वायर थीटा कहीं पे आ रहा है. And finally AX dash BX dash plus AY dash BY dash, it's same as AX BX plus AY BY. I will give you a minute to solve this. You already know the transformation. आपको derive करने की जरूरत नहीं है. I already know the transformation. AX dash क्या होगा? BX dash क्या होगा? AY dash क्या होगा? BY dash क्या होगा? in terms of ax, ay and theta. मैंने बताया क्या होगा, ax cos theta plus ay sin theta. This will be minus ax sin theta plus ay cos theta, and bx dash will be bx cos theta plus by sin theta, and by dash will be minus bx sin theta plus by cos theta. So I want you to multiply that ax dash bx dash and add to ay dash by dash. And I want you to prove this. This will be same as ax bx plus ay by. We'll just take 1 minute. I will give you a minute to solve this. ये भी देख लेते हैं ना, ax dash bx dash, पहला टर्म क्या होगा, ax bx cos square theta, एंड यहाँ पे देखो एक टर्म आ रहा है ax, ये दोनों माइनस है, माइनस माइनस प्लस ax bx sin square theta. I add both of that, that becomes ax bx. Similarly, I get ay by sin square theta, and I get here also ay by, कहाँ गया by sin square theta, कहाँ पे दिख रहा है, ay by sin square theta, I should get cos square theta, ay by cos square theta, ay by cos square theta, that becomes 1, and rest of all of the terms will become plus and minus, and they will cancel out. So it fits my definition of scalar, that under rotation the magnitude of scalar should remain the same, if as long as my origin is intact. That was the definition of scalar. Okay? Of course we know that for two vectors a and b, I get mod a, mod b, and cos theta, which has been measured by the standard rule how we measure angle between two vectors, right? I choose with one, go counterclockwise to the other. Okay, AB cos theta, which means that A dot B is always and always less than or equal to mod A, mod B, or simply AB. Can we see this? Because cos theta will always be either 1 or less than 1, right? So equality will only hold when theta is equal to 0 or theta is equal to pi. हम लिख सकते हैं. By the way, this is called Cauchy inequality. Now it may seem like that, ठीक है, this is very simple. Believe me, this is very very useful. जो Cauchy's inequality है बहुत useful है, because अभी तो मैं खाली वेक्टर यूक्लिडियन ज्योमेट्री में मैं डिफाइन कर रहा हूँ. लीनियर अलजेब्रा में हम n डायमेंशनल वेक्टर की हम बात करेंगे, हम n डायमेंशनल स्पेस एज्यूम करेंगे, एंड n डायमेंशनल स्पेस हम एक n डायमेंशनल वेक्टर वहाँ पे एज्यूम करेंगे, एंड देयर ऑल्सो Cauchy's inequality will fit, and that Cauchy's inequality will become one of the basis in proving, not exactly proving, but in deriving Heisenberg principle of uncertainty. So जो Cauchy inequality है, this has application in quantum mechanics. So it may seem like a very trivial per se, but this is actually quite useful in later part. And equality holds for theta is equal to 0 when vectors are parallel, or pi where vectors are anti-parallel. So A and B, or A and B. Only in these two cases A dot will be same as AB, right? Otherwise it will not be the case. We also know certain rules about dot product. For example, dot product is commutative. A dot B is B dot A, which makes a lot of sense because cos theta जो है वो cos theta is same as cos minus theta. We also know that if I take A dot product with sum of two other vectors, this is same as A dot B plus A dot C. We call this distributive property, that scalar product is also distributive. And one thing which is very, very useful, that if A dot B is 0, then तीन ही पॉसिबिलिटी है, चार पॉसिबिलिटी है, या तो A 0 है, B 0 है, दोनों 0 हैं, बट अगर दोनों नॉन 0 हैं, then the only possibility exists here is that they both are perpendicular. आप एग्जाम में ऐसे मत लिखना, मैं यहाँ पे लिख रहा हूँ, आप एग्जाम में या तो परपेंडिकुलर साइन बना के छोड़ दो या परपेंडिकुलर पूरा लिख देना, they both are perpendicular. This is very useful. Both are perpendicular. ठीक है. If you have any questions till now in the definition of vector, scalar, dot product, you can ask questions. They also follow transformation law. उनका ट्रांसफॉर्मेशन लॉ वेक्टर से थोड़ा सा अलग होगा. तो टेंसर डिपेंड करता है कि कौन सा रैंक है उसका, राइट? तो टेंसर का रैंक 2 है, रैंक 3 है, तो टेंसर के बारे में थोड़ा सा पढ़ेंगे हम. इन आवर डिस्कशन एटलीस्ट thrice or 3 or 4 times tensor will occur, and I will tell you about tensor and its transformation. But even for a tensor it will be a linear transformation, that how tensor from one coordinate to another coordinate changes, it will be a linear transformation. ठीक है? Any other question? Okay. There is a very interesting property. I wanted you to verify this. या इसको ऐसे verify करना भी आसान है. Imagine करो कि एक वेक्टर है, ये वेक्टर है, उसके दो कंपोनेंट्स हैं x and y में, ठीक है? I take a mirror, and because of that mirror, and this mirror is placed essentially, let's say this is x, this is y, so this mirror is placed parallel to y axis, and you immediately see that x axis is going to flip, ठीक है? This is now, let's call this x dash, but y dash will remain same as y, which means that in this new coordinate system, by the way, no rotation can transform from this to this. Can you appreciate that? That no rotation can go from here to here. This is not a rotation. मैं कुछ भी rotate करूँ तो मेरा x भी rotate होगा, y भी rotate होगा. This is called parity transformation. That I have essentially flipped sign of one of the axes. I have converted in 3 dimension. If I do the same thing, I go from right-handed to left-handed coordinate system. I will do that in 3 dimension. I will show you. But there is a very interesting property that even in this transformation, आपका जो definition of dot product है that holds true. आप इसको appreciate कर सकते हो. जैसे मान लो ये मेरा vector है A. Here इसके जो components हैं वो क्या हैं? AX and AY. By the way, whenever I use these 3 lines, what does that mean? I'm defining it. 3 lines का मतलब है I'm defining it. So I'm defining vector A as AX and AY. If I flip the coordinate system, then this A dash here essentially now becomes minus AX and AY. But look at all of the 3 scalars I can produce for A, B. So A square is AX square plus AY square. But here it is minus AX whole square, which is again AX square plus AY square. So my scalar is intact. Same thing for B. But even for A dot B, AX minus AX, BX minus BX. So minus AX into minus BX is plus AX BX. And AY BY तो same ही है. So जो मेरा definition of dot product है, the dot product is intact even if I'm using a left-handed coordinate system. This is interesting and important. But if I choose some other quantity, if I choose this quantity, let's say, तो एक तो मैंने ये quantity choose किया, ax bx plus ay by, and this is same as ax dash bx dash plus ay dash by dash. Under this transformation, I repeat, this transformation cannot occur by any rotation. This is only and only possible if I take a reflection along one of the axes. But if I choose another quantity, ax by minus ay bx, and इसका transformation देखो s dash में कैसा होगा. Ax will become minus ax, by will remain the same. So minus ax by. Ay will become minus ay dash, bx will remain the same. So minus ay dash, this is plus ay dash. So I get plus ay bx minus ax by. So that ये जो है, this becomes minus of this. In S, ये जो मेरा quantity है, in S dash, उसी का it becomes minus. Now this is useful in defining cross product. You already can see that in cross product, this occurs, right? So anyways, that is my next topic. But sorry, one more thing. I wanted to briefly talk about plane polar coordinate system. Give this heading. Plane polar coordinate system. Plane polar coordinate system. So again, I'm in 2D only, hence plane polar. XY. I take a point P. There are two ways to represent this. Represent the coordinate of that P, that I can represent that as xy. So this is vector r. I can write this r as x cap plus y cap. In Cartesian coordinate system, ये x and y का जो range है कहाँ से कहाँ तक जा सकता है? This is Cartesian components. इसको क्या बोलते हैं? What can be range of x and y? Minus infinity to plus infinity. X can be minus infinity plus infinity. So I can have minus infinity plus infinity. ठीक है. But there is one more way to define. ये जो x cap and y cap है, we call this Cartesian basis. Write down x cap and y cap. Cartesian basis in 2D. Basis का यहाँ पे क्या मतलब है? All vectors, write down, all vectors can be represented with x cap and y cap in two-dimensional space. X cap and y cap in two-dimensional space. Now again, it may seem like a very trivial statement. I do want you to give some basic glimpse of linear algebra, because right now I'm talking about two-dimensional space. So what this statement essentially means, that कोई भी vector हो, it will be some times x and some times y. यही होगा ना? 5 times x minus 3 times y, 10 times x 15 times y, कुछ भी random number हो. So these are two independent bases. मुझे two dimensional space में दो independent bases चाहिए. With help of only with x, I cannot represent all vectors in 2D. Only with y, I cannot do that. But x and y, which are independent of each other, they together can represent any vector in two-dimensional space. I also do not need more than 2. I just need 2 bases. This concept of basis is important. I will be using this concept in our discussion of quantum mechanics also. That we'll be using this concept of basis, use of basis, even in quantum mechanics. So anyways, we all are familiar with Cartesian system. If I have to represent constant x and constant y, what would that mean? Constant x will simply mean that I'm talking about a straight line which is parallel to y-axis. And what will constant y mean? That I'm talking about straight line parallel to x-axis. Okay? This is constant x. This is constant y. How do I represent length element and area element in Cartesian system? ये बहुत basic चीज़ें हैं. I'm not. This is something which you already have studied. So I go from here. I'm here at R, and I go to some R plus dr. Okay? This is R, and I go to R plus dr. तो इस dr को हम x and y cap में कैसे लिखेंगे हम? That dr will be nothing but dx x cap plus dy y cap. बहुत simple है, ठीक है? This is length element. What about area? If I have to choose an areal element in Cartesian system, what will I do? I will first vary x and then I will vary y. So when I vary x, that becomes dx. When I vary y, it becomes dy. So what would that look like? So I take x and then I take y and I make a small rectangle out of it. And ये जो rectangle का जो area है वो क्या हो जाएगा? dA will be dx dy. This is area element. Volume element हम 3-2D में दिखा नहीं सकते, तो volume element का यहाँ पे कोई मतलब नहीं है, ठीक है? I will be doing all of this in all coordinate system. How a length element will look like in spherical coordinate system, area element will look like in spherical coordinate system. So that is why being familiar with here right now is very useful. So now let's come to plane polar coordinate system. In plane polar coordinate system, there is one more way to write down that point P, which is this length r and this angle, let's call this phi. Okay, I'm going to use the word, I'm going to use phi. In fact, I should not even use r because I want to use r properly in spherical polar coordinate system. यहीं से हम शुरू कर लेते हैं. Let's not call it r. Let's call it rho. Because I want to use r in 3-dimensional system when I do use spherical polar coordinate system. So let's call this rho and phi. Rho is nothing but x square plus y square, and phi is nothing but tan inverse y by x. So my first question here is, so by the way, this phi is called azimuthal angle. (2D) में तो फिर भी मैं कुछ भी नहीं बोलूँ. I simply can call it phi coordinate, but in 3 dimension I will be using azimuthal angle, which will be different from polar angle. I will be using 2 angles in spherical polar coordinate system. So first thing first, what will be the range of rho? Rho कहाँ से कहाँ vary कर सकता है? It cannot vary from minus infinity. That was the point. It will be from 0 to infinity. Now I'm talking about distance from origin. So rho range will be from 0 to infinity, and phi where it can vary from 0 to 2 pi. ठीक है? Phi can vary from 0 to 2 pi. Either I take this or I take this. In fact, let me use this. 0 to 2 pi. आप लिख सकते हो rho and phi are called plane polar coordinates. Rho and phi are called plane polar coordinates. Plane polar coordinates. So we also know, of course, that x is equal to rho cos phi, and y is equal to, okay, you just tell me, I will give you 30 seconds to do this. What will constant rho and constant phi look like? Just the same way I talked about constant x and constant y, I mentioned that constant x will be a line, which essentially is nothing but parallel to y-axis, and constant y is a line parallel to x-axis. I will give you 30 seconds. What will constant rho and constant phi look like? Again, this visualization is important. I want all of you to visualize coordinate systems, different coordinate systems. We'll be dealing with different type of coordinate systems in problems. That visualization is important. What will constant rho look like? Draw constant rho and constant phi. I'll give you a minute. I'm just coming in a minute. A circle. That will be a circle. I am varying phi, but I am keeping my rho constant. Constant rho is nothing but circle. I am changing my phi. Now what will constant phi will look like? But I am changing rho. It will look like a half line. Can you appreciate that? I'm keeping phi constant. I start here, I go somewhere. This is my phi, and I'm changing rho. I can go anywhere. This is a half line, which has an origin, but it goes up to infinity. Okay? Half line. This is constant phi. I will ask this question everywhere. So ये visualization होना ज़रूरी है. अभी तो चलो ठीक है. I will ask this question in cylindrical polar coordinate system. I'll ask the same question in spherical polar coordinate system. That if I put one of that constant and I vary other, what it will look like. Okay? Anyways, what about unit vectors? This is now where things become interesting. Unit vectors in plane polar coordinate system. तो यहाँ पे जो मेरा बेसिस है वो क्या होगा? I am here at R, a row. ठीक है? So to make a unit vector for row, I have to take a unit value in that same direction of row. So this becomes my row cap. Okay? I will be using again this row cap. What about phi? So this is row, this is phi. What about phi? How should I take phi cap? What will phi cap look like? Phi cap will be पहले तो phi जो है, phi cap जो है वो एक यूनिक वेक्टर है which I have to get in phi's direction. But phi का direction क्या है? That is my question. So phi is increasing like this. Imagine ये यहाँ पे मैं एक सर्कल बना रहा हूँ ऐसे, ठीक है? Phi is increasing like this. तो ये मेरा phi क्या होगा? this will become phi cap. This is the increasing direction of phi. So you can see, and you can of course see from geometry, this radial direction and the tangent, they both are perpendicular to each other. So rho cap and phi cap will look like this. This becomes the basis, that same basis which I used in case of Cartesian system, that आप लिख सकते हो for a basis in plane polar coordinate, for a basis in plane polar coordinate, we can use rho cap. लिख सकते हो यहाँ पे, this is increasing rho, phi cap which is increasing phi. बहुत टेक्स्ट बुक में आपको ये ER E phi भाई दिखेगा, कहीं पे आपको AR, अगर आप इंजीनियरिंग टेक्स्ट बुक पढ़ोगे तो वहाँ पे तो ऐसे दिखेगा, यूनिट वेक्टर. जैसे कार्टेशियन सिस्टम में जनरली द मोस्ट पॉपुलर नोटेशन इज दिस I, J and K, but you can also find EX, EY, EZ. I use particularly this X cap, Y cap, Z cap. So there are different notations. In examination, sometimes UPSC has given this as AX, AY. So always remember that these are nothing but unit vectors. Whenever you come across this AX, AY, AZ, these are nothing but unit vectors. So anyways, coming back to this problem right now, that rho cap is that increasing rho, phi cap is increasing phi. But there is something very interesting about these two bases. In case of Cartesian basis, my x cap and y cap was fixed. Remember the definition of vector. I can put the same vector, I lift it here, without changing the magnitude, without changing the direction. If I put it somewhere else, it is the same vector. You all remember this? But so x cap and y cap are always same. What about rho cap and phi cap? Are they always same? Not at all. Because think about it. If I am here, then my rho cap is this. This and this is not same. These are two different unit vector. My phi cap is this. This and these are not same. This is a different unit vector. The point I am trying to make here is that in plane polar coordinate system, that rho cap and phi cap, they are not constant. Write it down. This is very important. Rho cap and phi cap are dependent upon where we are. Rho cap and phi cap are dependent upon where we are. Rho cap and phi cap very much will depend upon आपका coordinate क्या है. But x cap y cap के साथ नहीं था. X cap y cap was independent of coordinate. आप लिख सकते हो. While x cap and y cap are constant and independent of coordinate. Independent of coordinate. Why this is important? This will become clear once we start physics. I will start with basic kinematics. जैसे मान लो मुझे किसी वेक्टर को लिखना हो, कोई वेक्टर r है, I can simply write it as this as r cap. मुझे phi cap की जरूरत नहीं है. Can you see that? यहाँ पे मुझे किसी phi cap की जरूरत नहीं है. But the moment I take velocity, think about it. The moment I take dr by dt, then I have to take dr by dt r cap plus r dr cap by dt, because that r cap is also going to change. So this r cap is not constant at all. So this is very crucial, that in case of plane polar coordinate system, that r cap and phi cap, they are dependent upon coordinate system. Okay? So we'll be using this in later part of the discussion. Right now I want you to do two more problems. This will be the last two problems of today's class. That write ER and E phi, or R cap and phi cap, R cap and phi cap in terms of X cap and Y cap. ये चलो मैं करके बता देता हूं मैं. I'm here. Remember, X cap and Y cap are always same. They do not change. This is my X cap and this is my Y cap. ठीक है? But ER is this and E phi is this. So this is, or not use, I'm using R cap. So R cap is this and phi cap is this. And I know this angle. But I already know this transformation. I already know that at this point, this X cap, Y cap has been rotated by angle phi, and that has become R cap and phi cap, right? So I already know this transformation. What is that transformation? How can we write R cap? Cos phi. X cap cos phi plus Y cap. Now you can clearly see that if I take mod of it, this is cos square phi plus sin square phi, which is 1. So it is a unit vector. What about phi cap? This is minus X cap sin phi plus Y cap cos phi. ठीक है? लिख सकते हैं. So I have a relationship between how can we write R cap, phi cap. बहुत से और भी तरीके थे इसको करने के. हम R को लिख सकते थे x cos थीटा प्लस y sin थीटा, एंड यूनिट वेक्टर के लिए हम दोनों साइड R से डिवाइड कर देते, उससे भी हमारा हो जाता. ठीक है? that would also have a method. But I want you to do the problem, the opposite problem. Write X cap and Y cap in R cap and phi cap. Write X cap and Y cap in R cap and phi cap. ये सब जो भी मैं आज की क्लास में हम कर रहे हैं, यूपीएससी नहीं पूछेगी ये सब. ये बस हम हाथ खोल रहे हैं अपना, होता नहीं है. That we are again going back to the basics and doing some of the basics. सेम प्रॉब्लम को एक और तरीका था करने का. ये जो प्रॉब्लम मैंने अभी किया, and I want you to use that method in solving this. That essentially what I'm trying to do, I'm taking component of this R cap along X cap and Y cap. तो R cap का यूनिट क्या 1 है. R cap का वैल्यू मुझे पता है 1 है. 1 cos phi X cap. So 1 मुझे लिखने की जरूरत नहीं है, that becomes X cap cos phi. And 1 sin phi Y cap. So this is sin phi Y cap. And think about if I do that for phi cap. मुझे phi cap का component चाहिए on X and Y. So if I project phi cap on Y, then I simply get cos phi. Remember this is phi, so cos phi. But if I project this on X axis, I project it here. I project it here. So I'm going to minus X. So this is minus X cap sin phi cap. So use this method in figuring out this problem. आप सेम डायग्राम यूज कर सकते हो. अब बस अब आपको ऑपोजिट करना है. आपको एक्स कैप का कंपोनेंट चाहिए आर कैप और फाई कैप पे. आपको एक्स कैप को प्रोजेक्ट करना है आर कैप पे, और माइनस फाई कैप पे होगा. कैन यू अप्रिशिएट दैट? ये वाला जो मेरा एक्सिस होगा क्या हो जाएगा? ये डायरेक्शन हो जाएगा माइनस फाई कैप. सो एक्स कैप को आप प्रोजेक्ट करोगे आर कैप पे, दिस विल बिकम, so r, this essentially is 1, unit is 1, x cap का unit is 1 cos phi r cap and minus 1 sin phi cap. Can you see that? That 1 cos phi r cap minus 1 sin phi cap. And similarly do that for y cap. That what will be the components of y cap? So I can simply write this, that this x cap is cos phi r cap minus sin phi cap. And y cap, ये क्या होगा? sin phi r cap plus cos phi cap. कंफर्म कर लेना. है हमारे पास थोड़ा सा टाइम. एक प्रॉब्लम घर के लिए करते हैं. राइट डाउन अ प्रॉब्लम, घर पे करके देखना आप, मुझे ग्रुप पे आंसर करके भेज देना मुझे. फाइंड द एंगल बिटवीन फेस डायगोनल्स एंड बॉडी डायगोनल्स ऑफ अ क्यूब. Face diagonals and body diagonals of a cube. Simple problem है. I'll give you a hint. आपको वेक्टर लिखना पड़ेगा फेस डायगोनल का और बॉडी डायगोनल का, और उन दोनों का डॉट प्रोडक्ट लेना पड़ेगा cos थीटा. वहां से हमारा एंगल आ जाएगा. So take the dot product between these two vectors and you'll get the angle. ठीक है. Give this heading vectors in 3D. Vectors in 3D. First thing first, as I said earlier, in 3 dimension, I generally not, in fact most of the time, I'll be using this as xy plane. ठीक है. तो ये जो axis है यहाँ पे, ये जो axis है, this axis I will be taking as x axis, this axis I will be taking as y axis, and ये जो है, this axis I will be taking as z axis. In few cases, there will be a chance that this will be x, this will be y, and this will be z. But generally, this is the convention I'm going to follow. This is my xy plane, and this here is x axis, this here is y axis, this here is z axis. Okay? So the first thing first, that imagine this is my coordinate system, and I do, and imagine that, अब यहाँ पे तो imagine करो कि यहाँ पे कुछ origin है, and at this origin I make a very general transformation. It's a very general transformation, right? And in that general transformation, I have kept my origin intact, but that x becomes x dash. x यहाँ पे था, कुछ इधर आ गया, मान लो, ऐसे समझ लो कि x कुछ इधर आ गया है. This becomes x dash. This y becomes y dash, and this z becomes z dash. Z is also no longer on the board. Z has also come here somewhere, let's say here. Z is here, x is here, y is going inside the board little bit, right? So imagine something like that. Now rotation has happened. अब यहाँ पे देखो, दो information चाहिए मुझे about this rotation. पहला information तो मुझे ये चाहिए कि rotation कौन से direction के around हुआ है. I have kept my origin fixed. पहला तो information क्या होना चाहिए? That rotation कौन से direction के around हुआ है. First, and second, how much rotation has occurred. Can you appreciate that? That I need two set of information. That I need the unit vector, let's call this unit vector n, through which this rotation has occurred, and some angle psi, how much rotation has occurred. But I am very confident that this r has become r dash, because of this rotation, which essentially means that if I use, or आप ऐसे समझ लो, which essentially means that I can write this vector R equal to some transformation matrix R dash. This R here is rotation matrix, which is 3 by 3. And that rotation matrix will be now function of two things. It will be function of that n, the direction, and how much that rotation has occurred. I do not have to derive that. This will actually be a very complicated derivation. But the point I'm trying to make here is that whatever transformation I get for R, all other vectors have to follow the same transformation. Only then I will call that this particular quantity is a vector quantity. ठीक है? So ये जो R है, जो rotation matrix है, this will essentially depend upon that n and that psi, and that will be 3 by 3 matrix. And I can also guarantee you this will be a unitary matrix. That इसका अगर मैं determinant निकालूं, it will come out to be 1. ठीक है? But एक special case of course है मेरे पास, and that special case is that if I rotate it along z axis. Imagine मेरा ये axis है and ये मेरा मान लो मेरा z axis है, तो मैंने z axis को intact रखा है and मैंने बस खाली इसको rotate किया है. So I have kept my z axis intact and I have only rotated x and y. So in that case I can write this 3 by 3 matrix, what this will look like. मान लो ये मेरा ये x है, y है, z है. I have kept z intact. My rotation is along z axis, but I have changed x, I have changed y. This is x dash and this is y dash. And let's say this change has occurred by angle psi. So you can now clearly see that जो मेरा rotation matrix है, पहले तो this is a function of Ez cap or z cap and psi, and this is cos psi, sin psi, 0, minus sin psi, cos psi, 0, 0, 0, 1. अभी clearly confirm कर सकते हो that because of this rotation, if x has become x dash, y has become y dash, z has become z dash. And this is the rotation, cos psi, sin psi, 0, minus sin psi, cos psi, 0, 0, 0, 1, x, y, z. अभी कंफर्म करके देख लो. x dash will be x cos psi plus y sin psi plus z into 0, right? Y dash will be minus x, so minus x sin psi, y cos psi, z into 0. And z dash will be 0 into x, 0 into y, 0 into x, 0 into x, 0 into y, and 1 into z. So z dash will be z. So in this very special case, this is how your rotation matrix will look like. And any vector will follow the same transformation rule. That is my definition of vector into 3-dimensional basis. ठीक है? यहाँ पे मेरा length element, area element and volume element क्या दिखेगा? In Cartesian system, अच्छा by the way Cartesian system में जो dot product है, dot product a dot b, that will be ax bx, ay by plus az bz, which will be same as mod a, mod b, and the angle between them. We already know this, right? What about other things? For example, what about the length element? I am at R and I make some, so this R is somewhere here. Let's say this is my R, ये मेरा कोई R है, and this R I go in this direction. dr. I make a change dr, but now this dr will have three components, dx, dy and dz. तो मेरा dr क्या होगा? dx x cap, dy y cap plus dz z cap. This is my length element. What about area element? I can get three areal elements, can't I? Either I am changing x and y or y and z or x and z. So dA1 will be dx dy. Do you guys, I am very sure you already know that area can be treated as a vector, right? So in this case dx dy, that vector, उसका direction कहाँ पे होगा? Z के round. Z के round होगा. dx dy rotate करेंगे, that will turn out to be z. Right now I'm not using it, but in later classes in electricity and magnetism we'll be using this. dA2 dyz and di3 dz dx. And what about volume element? Very simple. I can make a cuboid by first changing x, then changing y, and then changing z. Okay? So my volume element d tau will be dx dy dz. Distance between 2 points, very close to each other, that will be dx square dy square dz square. Same thing Cartesian system, that will be dx square plus dy square. So before I conclude today's class, I forgot to do one very simple exercise, which is that what about areal element in plane polar coordinate system? I will give you some time, that what will area element in plane polar coordinate system will look like. And for that matter, distance between 2 points. I'll go back to two-dimensional system. I have x, I have y. This is my r and rho and phi. So I mentioned few things, that dA will be dx dy. ds will be square root of dx square plus dy square. Okay? Same thing in Cartesian system, in plane polar coordinate system, these two things what they will look like. I will give you a few minutes to solve this. I will give you one more hint. जब भी हम फिजिक्स करेंगे, चूंकि हमारे सिलेबस में डायमेंशनल एनालिसिस अलग से दे नहीं रखा है, तो हम कर नहीं रहे हैं, बट ऑलवेज रिमेंबर कि डायमेंशनल एनालिसिस जो आपने पढ़ा होगा, एच सी वर्मा भी पढ़ोगे तो पहला चैप्टर क्या है? डायमेंशनल एनालिसिस है. आपको लगा होगा कि बड़ा सिंपल है, क्या ही कर रहे हैं, बहुत पावरफुल है. Dimensional analysis is such a powerful tool and it can help you in such complicated problem that you will always be amazed. As a student of physics, आपको बस ये ध्यान रखना है कि whatever you are writing, whatever equations you are writing, the left hand side and right hand side should have same dimension. इसका आप हमेशा ध्यान रखोगे, right? Left hand side, right hand side same dimension होना चाहिए. With that in mind, last two questions of today's class. I will end today's class after that. We'll do cross product and triple products and cylindrical and spherical polar coordinate system in the next class. But the last topic of today's class, that how will we write areal element and that distance between 2 points, that distance element. वेक्टर तो हमने लिख लिया था dx x cap plus dy y cap, तो ds जो है that is nothing but square of this. How will we do the same thing in plane polar coordinate system? आर के डायरेक्शन में चेंज करेंगे, फाई के डायरेक्शन में चेंज करेंगे, एंड इन फाई डायरेक्शन जो मेरा चेंज होगा वो लेंथ एलिमेंट कैसा दिखेगा. दिस इज व्हाट वी हैव टू फिगर आउट. क्या है आंसर? आप ऐसे देख लीजिए. अच्छा, by the way, before I forget, I should have done in the starting of the class. I know that a lot of students who will appear in final exam, and after that you'll join this optional batch. So please send me a mail. Please send me a mail, your name, your student ID, and your phone number, because I'm going to add you to a WhatsApp group which we have made, where we will keep discussing class assignments and PYQs. I will be giving you some questions, and to save time I will simply ask you to like post this on the group itself, and at the group itself we will discuss how we could further improve in different questions. So if you join this, if you watch this recorded lecture later, please send me a mail, your name, and please don't forget your student ID, that is important, and your phone number, where WhatsApp has to work. And I'm going to add to a WhatsApp group. We will be in constant communication even after the class. Sometimes we'll be using that group for class assignments and homeworks. So anyways, I make a random directional change. I'm here, I make a random directional change. I go here. So if I take this component on dx and dy, that was very simple. But here, if I have to take this component, remember, I first have to see that how that r has changed. So r has become r plus dr. And I also have to change how that phi has changed. So r has become r plus dr, and that phi has changed phi plus d phi. So ये angle मेरा क्या है? d phi. तो ये जो ds है, if I take its component, the displacement, if I take its component on r, then that is nothing but dr. But if I take its component on phi, it is r d phi. Can you appreciate that? ये जो length है मेरा, look at this particular length. I have kept my r, magnitude of r is same here. And that phi has changed from phi to phi plus d phi. So what will be this arc length? It is nothing but r d phi. As long as this d phi is a very small value, I can think of this as r d phi. So ds will be dr whole square plus r d phi whole square. And that same thing will be also area. Let me make another diagram. Aerial element को समझना बहुत आसान है उससे. I want to make a rectangle by first varying dr and then by varying phi. So I take r, this is my r, and I change r to r plus dr, which is this length. Okay? But then I have to make a rectangle. So, and then I change phi to phi plus d phi. Okay? So this is r plus dr, and this is, अब ये जो मेरा लेंथ है, ये लेंथ क्या है? r d phi. And ये लेंथ मेरा क्या है? dr. So this aerial element, what is this? dA. dA is r dr d phi. And you can see that this is dimensionally correct. dA, what will be the dimension? Meter square. R, dimension of length. Dimension of length, d phi, what is the dimension? It's a dimensionless quantity. Remember, the radian hai, that is nothing but ratio of two length. So d phi is this by this. So it has no dimension. So area, area. I am correct. Last question. 1 minute. Using this aerial element, prove that circle का area pi r square होगा. करके देखो. And circumference 2 pi r होगा. Do all of this problem. Do both of the problem. Using what I just discussed here, I want you to prove that circle's area will be pi r square and circle circumference will be 2 pi r. Of course integrate करना है, वही करना है हमको. Integrate करना है हमको. आप मुझे बस जानना है कि आप इंटीग्रेशन लिमिट कैसे कर रहे हो. The correct way to do this problem will be, I've given you a circle of radius capital R. Okay? I have to calculate its area. So I'll first choose an areal element at some R and some phi. I choose this dA. What did I tell you? dA is nothing but R dr d phi. Because how did I choose it? I first changed R to R plus dr, and then I changed phi to phi plus d phi. So this length became dr, and this length became R d phi. So R dr d phi. And then I have to calculate the total area, I have to integrate this. What will be my integration limit? From where to where R is varying? R is varying from 0 to capital R, R dr. And remember, R and phi are not dependent upon each other. So this will be a double integration. I have two variables here. This will be a double integration. R dr and 0 to phi d phi. I can easily separate it because R and phi are two independent variables. अगर ये independent नहीं होता तो मैं separate नहीं कर पाता. फिर मुझे R and phi को interchange करके लिखना पड़ता. So this is nothing but 0 to 2 pi, sorry. Phi कहाँ से कहाँ तक जाएगा? I start from here, I take one complete rotation, I go to 2 pi. R कहाँ से कहाँ तक जाएगा? From 0 to capital R. 0 to capital R and 0 to 2 pi. ये क्या है? This is R square by 2 into 2 pi. What is the answer? Pi R square. Area is pi R square. For circumference पे remember I only have to calculate the perimeter. So the moment I have to calculate perimeter, that length is fixed. That length is already, I know, capital R. So all I have to do, I have to choose a small elemental length at angle phi and phi plus d phi. So I have to choose this length. This length will be R d phi. And इसी R d phi को मुझे क्या करना है? Integrate करना है from 0 to 2 pi. What is the answer? 2 pi R. ठीक है? So this seems like a trivial problem, but this use of elemental area, elemental volume, ये हम moment of inertia calculate करेंगे, electric field calculate करेंगे, gravitational potential calculate करेंगे, ये हर जगह आते रहेगा. So use of elemental area, elemental volume, हम जितना पहले clear हो हमारे दिमाग में उतना better है. In next class, तो अभी तो हम फिर भी simple चीजें कर रहे हैं, like we are doing that in 2-dimensional system. We will do the same thing in 3-dimensional system, in spherical polar coordinate system, how elemental area will look like. And I do not want you to mug it up. I should be very clear about it here. Not for a moment. If you feel that you're not able to visualize it, ask me, ask questions to me. I will give you, I have like a lot of, I have not shown you any slide. I have a lot of slides which I can show you for further visualization, that how things will look like. This is what I meant, that I changed R to R plus dr and phi to phi plus d phi. And this becomes my areal element R dr d phi. I have a lot of visualizations. Triple product क्या होगा? ये spherical polar coordinates. So we will talk about this. But I do want you to first try to visualize things by yourself. So in the next class, we'll continue this discussion. And we will talk about first cross product. That will be the starting point. And then we will talk about triple products, scalar triple products and vector triple products. And then we will talk about other coordinate system, because right now we have only talked about Cartesian systems and in 2D plane polar coordinate system. So in 3D, how do we use other coordinate system apart from Cartesian system? That will be our discussion in the next class. I'll see you guys in the next class. Please do some of the homework.